Hey everyone and welcome back to PrepFusion. I am Anish and today we'll start the lecture 4 of our Magnetostatics chapter. Up until now we have studied about magnetic field, Ampere's law, magnetic force. So in this lecture we'll study about magnetic flux because I've taught you about magnetic flux density, but I haven't taught you what is magnetic flux, same as electric flux. Okay, but there are few differences that we'll come to. And obviously we learn about a new type of potential known as magnetic vector potential. As electrostatic has its own electric field, electric potential or potential difference, magnetostatic also has its own potential known as magnetic vector potential. Okay, this is just a term, that's it. Okay, this has no real physical significance. I couldn't find any real physical significance except to find the values. Okay, and then obviously we learn about boundary conditions for magnetic fields. What are the different boundary conditions for magnetic field for between two boundaries? Okay, so before starting that, obviously I gave you a homework. This question was homework, right, for an infinite sheet. So we'll solve this question. So here we had two large metal sheets carry electric currents along their surfaces. Okay, so they have large metal sheets which carry electric current along their surfaces with a current per unit length of K. So basically the surface current density has been given to us. So surface current density has been given to us and the direction is also mentioned, right? Direction is coming towards me. So I will take care of the direction later on. Okay. Determine the magnetic field at a point P located on the same side of both sheets. Okay. So if the if the point P is located here at the middle and for case 2 it is located at the outside, what will be the magnetic field? Okay. So I told you, remember this formula that magnetic field for a infinite sheet was mu magnitude of the surface current density divided by 2. Direction I can take care later. Okay, so I'm observing this for the first case. I'm observing due to this, right? If I see at this point P, if I just place the thumb along the direction of the fingers and curl my fingers, I see it is on the right hand side. So due to this, the top right hand side, the magnetic field is on the right hand side. Okay, and due to the bottom one, where is the magnetic field? Magnetic field is if I just curl my fingers, okay, and then if I place my thumb along the direction of the current and curl my fingers, it is along this direction, right, left. And one more interesting fact, we saw that this magnetic field, right, it was independent of distance. There was no distance present. Okay, this magnetic field was constant. So this I forgot to mention yesterday, that this is constant magnetic field, independent. Okay, independent of distance. Now you must say, sir, then we can increase the K whatever we want and we'll get infinite amount of magnetic field. That is true, but is it possible to get an infinite sheet with current flowing, right? That is also not possible. So that's why things like this come. We are just studying theoretically, then with the help of this we'll do the practical approximations. So both in opposite direction. What will be the magnitude? Both of them carry unit length, or both of them have surface current density K. So the net magnetic field B net will be basically B1, magnitude of B1 minus magnitude of B2, as magnitude of both of them are same, so it will be simply 0. Okay, so the first one, it is simply 0. Okay, for the first one, option D will be the correct one. Okay, none of the above. Now let's do it for the second one. If I just bring this, it will be like this. Second one also will be very, very simple. You can just place this at the top. Okay, for the second one, what I observe is that the point is at the top. Okay, so due to this bottom one, again, if I curl my fingers, I will see the direction at the top. It is going leftwards, right? It is left, B1. And for this bottom sheet as well, again, if I curl my fingers, it is again going leftwards. B2. So both are actually getting applied along same direction. So this time my B net will be magnitude of B1 plus magnitude of B2. I'm just concerned about magnitude for now. So it will be equals to, for a single sheet it was K, magnitude of K by 2, mu magnitude of K by 2. For a for two sheets it will be mu naught K divided by 2 into 2. So simply it will be mu naught into K. So it will be option A. So in this case, option A will be the correct answer. Like, this is very simple question. This type of question can come GATE examination for 1 marks. Okay, that's it. They can just simply ask the concept. Okay, so now we'll start today's lecture. First of all, we will start with simply magnetic flux. So it's same as electric flux. Nothing is like fancy here. Just few new things we need to study. Magnetic flux is a measure of quantity of magnetic field lines passing through a given surface area. How much field lines crosses through a given area, that is the meaning of magnetic flux. Same as electric flux, right? Their electric field, how much electric field lines cross the particular given area. It quantifies the total magnetic field that passes through a specified area, and it is expressed mathematically as surface integration of B dot ds. That's it. Okay, unit is the SI unit of magnetic flux is Weber, and which is equivalent to Tesla meter square, because unit of magnetic field magnetic flux density is Tesla, and meter square is unit of surface. Now there are two things of flux, same as the previous in the electric flux thing. Flux through open surface. For open surface, the magnetic flux is calculated by integrating the magnetic field over the surface area. The orientation of the surface relative to the magnetic flux affects the total flux value. Okay, so some orientation has to be given, especially if the field is not uniform. So the orientation has to be given if we have to compute the magnetic flux, whether it will be positive or negative. Just a sign change will come, just same as the the electric flux. But if the closed surface is given, then obviously we can find out the direction of the area vector, which will be pointing outwards from the closed volume. But if open surface is given, they need to provide the orientation of open surface. Then only I will be able to comment about the sign of the flux. Magnitude I can comment, right? Magnitude I can comment, but the sign I won't be able to comment because orientation is not given. I don't know what is positive and what is negative. I can assume my own reference and solve, and I will get some value. That value can be positive or negative. But orientation, if orientation is given, I can directly say that value according to the orientation it should be positive or negative. Okay, so what are the factors affecting magnetic flux? Same as electric flux. Magnetic field strength, obviously if the higher the magnetic field, right, higher the field lines, the more the flux I will get. Area orientation, if the area is at angle is theta, then I will get less flux. If area is perpendicular, then the area vector and the magnetic field lines will also be perpendicular, so I'll get more flux, because here I have dot ds cos theta, cos of angle. As theta goes up, the cos theta goes down, so that's why theta needs to be less. And same as surface area, if the surface area itself is larger, so I'll get more flux. These three things are general, so I am not going too much in depth here because we have already studied electric flux and same thing only. But just remember this, like same thing as electric flux. We have to, like, what does this actually mean in layman terms? In layman terms, number of magnetic field lines that cross with perpendicular area of the given surface. Okay, so that is what magnetic flux means. And one important property is about the closed flux. What will be the total flux through a closed surface if I have magnetic field like this? So how do you compute the flux? Now, what was the formula? The formula was this, right? Finite was integration. Now this will become a closed surface integration, right? Because this is a closed surface. I am just computing the flux through a closed surface. This will be B dot ds closed surface S. Okay, this is the surface S. Now what I can use the Gauss's divergence theorem. So if I use the Gauss's divergence theorem, what I will get, this will be equals to triple integration del dot B dV. And what do I know about del dot B? I know that my magnetic field is solenoidal. Solenoidal meaning that the divergence of magnetic field will be 0 because it doesn't have any source or sink, right? Wherever it exists, it exists with a source and sink. It's always a dipole. It's not a monopole. Okay, so here I can visually see as well. So if some flux enters here, the same flux will go out because it's in a loop, right? Generally magnetic flux is in a loop. So whatever enters, that same flux will go out from the other surface. So no net flux is inside the closed surface. So this will be equal to 0. So our things become very simpler. If ever in the examination they ask what is the net flux and the surface is a closed surface, then you can, without doing anything, you can directly say it will be 0. But this thing remember, this thing is only valid for non-time varying fields. Okay, if the field is time varying, then things will change. Okay, please remember, not a function of time. It should not be a function of time. If it is a function of time, then obviously things will change. But if it is not a function of time, which is in our syllabus, function of time is not in our syllabus. Okay, so it will not be in our syllabus, and they will not ask that. If it is not a function of time, then it will be always 0. Same for electric fields as well. It was irrotational that we derived. If electric field was function of time, then that wouldn't be true. Okay, del cross E won't be 0. But obviously, whatever in the examination they will ask, in our syllabus we have electric fields which are not function of time and magnetic fields which are not function of time. Okay, so generally that thing won't get asked. Okay, so this always the net flux will be 0 without even lifting the pen or solving anything. You can directly solve. Okay. Now, a new term known as magnetic vector potential. We need to learn about this term. So this is just to express the potential in magnetic fields. The magnetic field V can be expressed in terms of magnetic vector potential A, like this. Okay, so B is equals to del cross A, where A is the magnetic vector potential, B is the electric flux magnetic flux density. Okay, so just you should know about this term, that how to find out magnetic vector potential. And one of the property that we can find out of magnetic vector potential, if I do the divergence of curl of magnetic vector potential, I will get a null vector. How? If I take the divergence on both sides in this equation, del dot B equals to del dot del cross A. Then what do I know? I know del dot B is again divergence of magnetic field is 0, so this will be equals to 0. So whenever, if in the question they ever ask, will this be a valid magnetic vector potential function, then I have to take the curl and then have to take the divergence. Then I will be able to tell if I get a null vector, right? If I get a null vector, then I can say that yes, not null vector, sorry, if I get 0, then I can say yes, it is possible that that function can be a magnetic vector potential of a magnetic field. So yeah, that was the few things that I want to talk. And why we actually define this term? To help us in what? In computing the flux. That's what engineers do. They just define few new terms to make the computations simple. So now if I want to compute the flux psi m through a open surface, okay, so that will be equals to what? That will be simply equals to the integration of B dot ds. Okay, that is equals to what? Now what is B? B is del dot del dot not del cross A into ds. Correct? Now can I go reverse from here? Is this looking something familiar? This is like the Stokes theorem. If I would have applied the Stokes theorem through a closed enclosed line, okay, then I would have got this expression, right? Open surface integration of the curl of that particular vector. So I can apply the inverse Stokes theorem. So this will be inverse Stokes theorem. This becomes A dot dl. Okay, this is what? Inverse Stokes theorem. Okay, so that's why I wrote my magnetic field like del cross A to just apply this concept. Just simply do this to apply the inverse Stokes theorem. I just written my magnetic field in terms of del cross A. Now you might have your confusion. Why did I do this? Exactly due to that. Okay, due to this reason, engineers do define a new term. Okay, so we will see with the questions how it helps us. Okay, so given a magnetic vector potential A, calculate the magnetic flux density at a point -1, 2, 5. We have to calculate the magnetic flux density if magnetic vector potential is given. So we can simply do what? We can simply do the del cross A, right? So for the first case, I have to first of all find out the magnetic field flux density, right? Magnetic flux density is del cross A. So I will just take the curl of this. So it will be AX, AY, AZ, del X, del Y, del Z. So this will be X square Y, Y square X, X square Y, Y square X, and minus 4XYZ. This will take some space actually. Minus 4XYZ. Okay. So now if I solve it, this will be minus 4XZ. XZ, and this will be simply 0. So minus 4XZ AX cap. Then this will be minus 4YZ, and minus is already there, minus 4YZ. This is gone, and this is also again 0, right? This will be 0. AY cap plus. Now this is Y square minus X square. Y square minus X square. Is it cap? So now what I will do, I'll just simply put the values. What was the values? It was -1, 2, 5, right? So I will just tidy this one up. This will be minus 4XZ AX plus 4YZ AY plus Y square minus X square AZ, and it is 1, -1, 2, 5. Okay, so if I put this value here, it will be -1 -1, this is 5 AX plus 4 into 2 into 5 AY plus Y square is 4 minus X square. So this will be -1 AZ. So have they asked? What have they asked? They just asked us to find a magnetic field flux density. So this one will come out to 420 AX plus 40 AY plus 3 AZ. Okay, so this will be the basically magnetic flux density for the particular field at some point -1, 2, 5. Okay, now what are they asking? They are asking us to find a magnetic flux crossing through a surface z equals to 0, x going from 0 to 1, y going from -1 to 4. Okay, so This surface is what? Can you tell me what is this surface? This is just a simple square plane, right? This is a simple square plane. Okay, so if I try to draw this circuit, just draw this thing, this whole thing will come up, right? Can log this actually here. Let me draw the XYZ. This one. So the surface is x is going from 0 to 1. Okay, so it's somewhere at z equals to 1. It is going from 0 to 1. Then what happens? I start from, and y is varying from -1 to 4. Okay, so I'll start from somewhere here, -1 to 4. Okay, fine. Somewhat like this. It will just be the duplicate of this. So like here, right, they haven't mentioned the orientation, so I don't know what is the orientation. Okay, so that is the important point, if it will be positive or negative. So some orientation has to be mentioned. So I will assume my orientation like this, from here, and y is going from -1 to 4, like this and like this. Assume a orientation. Assume a orientation, like what as orientation you can assume is, you can find out like the magnetic field is always positive, so you can assume in the positive direction some orientation, right? So assume a orientation of the closed curve. Okay, now I can find out the flux using two methods. One is using electric flux density, another one is simply using the magnetic potential. So I will solve it using two methods. Okay, so method 1, using B. So first of all, what is my area vector? Area vector direction will be like this. It is in the plus AZ cap direction, right? And like, what is the differential surface ds? Ds will be simply dx dy AZ cap. Okay, so it will be equals to so my flux, right, psi magnetic flux will be equals to integration double integration. Do notice that my z is not varying, z is equals to 1. Okay, my x is varying, right? So I will replace my b here, right? I got my b function here, so that I will replace, and only I have along AZ cap, so only I will solve for AZ cap. Okay, because the dot product due to all the other, it will be 0. AZ dot AY 0, AZ dot AX 0, so only this one will be present, right? So we write here, this will be equals to b dot ds integration, as the AZ cap is only present, all the other components will be simply 0 AZ. Where is my x and y varying? X is going from 0 to 1, and y is going from -1 to 4. So here my phi m becomes what? Phi m becomes this, right? This integration y equals to -1 to 4 0. So if I will integrate this, this will become y square x minus x cube by 3 0 to 1 dy. So here it will become simply integration y equals to minus 1 to 4 1 to 0, right? So it will be simply y square minus 1 by 3 dy. So it will be simply using what is it, simply y cube divided by 3 minus y divided by 3 minus 1 to 4. So this will be 4 cube, that is 64 divided by 3, 64 minus 4 divided by 3 minus of minus 1 plus 1 divided by 3. So it actually comes out to be 20 webers, and we have like assigned a direction, right? It was plus az cap direction, we had assigned a direction. Yeah, sorry for the interruption, a call came up. So I will just solve it using the second method. Second method is using E dot dl, closed line integration of E dot dl. So this will be equals to what is, I just computed my A, right? Like A was already given to me in the question. Now if in the question only A was given and this first part was not there, then you would have directly solved using A dot dl. But as they have asked the first part as well, and from there I can identify that the magnetic flux density relation is much easier, because it is in az cap direction and my surface is also in the az cap direction. So I will solve using method 1. If these two questions were present, right, both part 1 and part 2, if only part 2 was present, I would have solved using the method 2. Okay, so what is my A? A is this, right? I'll just copy this A. Now what is my DL here? What is my DL? DL is simply a, if I just see, DL is simply a rectangle like shape, right? DL is simply rectangle like shape. It will take us time, but it's fine. We should learn both ways. Again, we have done this multiple times, how to compute the line integration. This thing we have done hundreds of times, right? So I will divide this into sections. So there will be section 1, one, 2, 3, 4. Okay, so it will be A dot dl for the first part, A dot dl for the second part, and so on. I will just duplicate this. Okay, so that is the case here. 4. So now what I can say is this like in this first curve, right, what is constant in this first curve? Actually my z is constant and my x is also constant. So obviously for this first curve I can say my dx and dz both are 0. For this second one, what are 0? For the second one I can observe that I am only varying in dx, right? So I can write it in shorter manner, that my, in this case for curve 1, my dy is non-zero. For the curve 2, my dx is non-zero. For the curve 3, my again dy is non-zero. For the curve 4, again the same thing, only dx is non-zero, right? Dz is anyways always 0. Okay, so this will not be that difficult as it seems. So here I can write down my flux. Okay, I'm not able to, what is happening with me? Flux will be the first, for the first case my dy is non-zero. If my dy is non-zero, what, like I will only choose the y component, right? Only choose the y component. So integration y square x dy. Okay, and my y is varying from -1, y is varying from -1 to 4. If you remember, this was the thing, right? Y was varying from Where did it go? Okay, y is going from -1 to 4. Somewhere I copied it, I think. Somewhere I copied, or I didn't. So it will go from -1 to 4. Next, for the second part, again my dx is non-zero, so I will only take the ax component, right? Because ax dot ax will be non-zero, ay dot ax, all other components will be 0. So x square y dx plus, now x is varying from what? X is varying from 0 to 1. From what I remember, it was from 0 to 1. 0 to 1, yeah, 0 to 1, z is equals to 1. So I'll just simply copy this thing. I don't know where I kept it. Somewhere for my convenience, I will paste it over here. Okay, so z is going from in the third case again, this will be dy. In the third curve, this will be dy again, but this time I'm going from 4 to -1. Okay, 4 to -1, and the values are different. Here what is my x? Here my x is equals to, in this region my x is equals to what? X is simply, in this particular case, right, x is simply equals to 1. Okay, x is equals to 1. So here x will be equals to 1. Here my y will be equals to what? Y will be equals to 4. The final stage, right? Y will be equals to 4. Here again it will be y square into x dy, but my x itself, currently I'm lying here in this curve, and at this curve the x is 0. X value is 0 simply. So x will be simply 0. Okay, have I made any mistake? No, x will be, just hold on, sorry, if I'm moving from here to here, my x here is actually 1. Okay, I'm from here, right, I'm moving from x equals to 1 to 0, so this limits are wrong actually. This limit should be, just hold on, limits are wrong. This should be from 1 to 0. Okay, and this should be from 4 to -1, correct? Here my x is 0 because here my x has reached 0, right? And for the next case, it will be from x equals to 0 to x equals to 1, 0 to x equals to 1, x square y, and my x is equals to what? X is equals to, y is equals to what? Y is equals to -1. Okay, dx. So now I can simply compute all these things. So my overall flux, this one will become y cube by 3, y cube by 3 -1 to 4 plus this one will become 4x cube by 3 1 to 0. This one will be 0 simply because x is 0, and this one will be, here y is -1, so minus x cube by 3 0 to 1. Okay, so overall what it becomes actually, so this one is 4 cube, that is 64, -1 becomes plus 1 by 3. This one becomes minus 4 by 3, and this one becomes minus 1 by 3. Okay, so overall it becomes 20 Weber. We get back the same answer. Okay, so you just observe, like at first it may seem intimidating, all these line integrations, but actually it is not. Sometimes this will be easier, sometimes the other one will be easier. You have to understand which one is easier to you. Okay, most cases dx dy will always be 0. So I'll not explain how am I doing this line integration, because this has been taught in vector calculus very well. Okay, very well, we have taught this in vector calculus. Okay, so that is the case. So now let's solve another question. Okay, in this question we have to determine the magnetic flux crossing through the surface at this particular surface this. So here if you observe, there is two are variables and one is fixed, so we will get a 2D structure. We'll get a surface basically if the magnetic vector potential is given as A. Okay, so there are two ways to go about it. Either if you do del cross A, then you find out the magnetic flux density, then you integrate that with respect to the surface, you will be able to find out. Or what you can do with the help of E dot dl. Okay, what you can do, method 1, that I will leave you to as homework. Method 1 is you do del cross B. Okay, del cross B, and not del cross B, sorry, you do B equals to del cross A, then you find out B, then you integrate B through this surface B dot ds, and you find out the flux. Okay, but the interesting fact is that let's say if you forgot right, what was the curl of a in the cylindrical coordinate system, then you can take help of the line integral, because remembering the line integral is the most easiest thing. So I'll use the method 2. So in method 2, what I'll do, I'll directly apply this formula, that magnetic flux is equals to A dot dl whole closed line integration of the enclosed curve that the surface is covering. Okay, so open surface is covering. So what is the surface? So to identify the surface, I have to obviously understand this variables, right? So I will just copy and paste this thing, and I will draw a axis. I will draw the cylindrical coordinates. So I can take help of the previous coordinates and just copy this thing, or I can copy, okay, this one I can copy, yeah. So here what I am observing, that this phi is constant, so I am always at 90 degrees, that is in the y axis. Phi is constant, right? My rho is varying from 1 to 2, so rho is varying from rho equals to 1 to rho equals to 2, and my z is going from 0 to 2. So this is also a like a rectangular shape only. Z is going from 0 to 2. So the surface will be something like this. This is the surface. Again, I have to assume a orientation. So again, I will assume some orientation according to my convenience, and if the flux comes out to be negative, that's fine. So I have assumed this orientation, and if like they should mention the orientation, if they haven't, then I will assume this orientation, right? So this is the orientation basically, and what will be the direction? Direction will be perpendicular to this, so it will be in this direction, correct? What is this direction? This is plus ax cap direction. Okay, ax cap direction, or in our case, yeah, flux will be in this plus ax cap direction only. If you want to write ax in terms of a rho a phi, and you can do that. So now we will solve this. So how do I solve? First of all, I will write the dl in cylindrical coordinate system. What is it? It is equals to d rho e rho plus d phi, not simply d phi, it was rho d phi, rho d phi a phi plus dz az. Okay, so what will I understand here? So for the first case, for the like I can break this down, right? I can break this down basically. Now I will delete these things. So in this case, what is non-zero? What is non-zero basically? In this case, in the let me name the curves. Again, I will break down the curves, right? 1, 2, 3, 2. So here my d rho is non-zero. Here my dz is non-zero. Here again the same thing, d rho is non-zero, and here the same thing again, dz is non-zero. So I can break this down further, and my a right is only in the az cap direction. A is only in the az cap direction. So I won't even care about the other directions. So here, which direction I'm going, dz non-zero. So this component I will take, right? This I won't even consider, because this will be 0. So I can safely say, because what is the direction? Arrow cap dot az cap is what? 0. So the dot product itself will be 0. So I can safely say that phi m will be integration of a dot dl 1 plus integration of a dot dl 2 plus integration of a dot dl 3 plus integration of a dot dl 4. And out of this will be simply 0. Why? Because this is d rho, right? Here d rho, this is in the direction of aero cap. Aero cap dot az cap will be simply 0, and this also will be simply 0. Okay, because aero dot az is 0. This will be non-zero because it has az cap, and this also will be non-zero. And in this both cases, rho value is fixed. Okay, so what I can do is I can simply write down the values here. So in this case, what is the rho value? Rho value in this case, right? I'm on the curve 2. Curve 2 is here. Rho is 2. Here rho was 2, right? If you remember, rho was 2. So in this case, rho is 2. In this case, fourth curve, here rho is 1 basically. Rho is 1. So psi m will be integration a is what? Rho cube by 4. So here rho cube, not rho square by 4. So this is 2. 2 square by 4 is simply 1 itself, that is az cap dot dz az cap, and z is going from where? Z is going from 0 to 1. Sorry, not 0 to 1, 0 to 2. Z is going from 0 to 2. Plus next time z is going from 2 to 0, and here rho is 1. So this will be 1 by 2 az cap dot dz az. So this will become actually 2 plus this will become 1 by 2 is there. Okay, rho 1, yeah, square by, okay, it was 4, sorry, it was 4. So this will be 2 by 4, which is 1 by 2 minus 1 by 2. So this will come out to 1.5 minus 1.5 Weber, plus 1.5 Weber. So whatever direction I assume, right? My assumption is electric field, like orientation of the surface is this, and flux is crossing like this. That is my assumption, right? So if flux crosses like this, that was my initial assumption, and that was correct. So I got 1.5 Webers. Okay, so whichever orientation you can choose, and you will get back your same answer by using this concept as well. But if you get negative, right, then the orientation may have been something different. That's it. Magnitude of flux we know. So now basically we will start with the boundary conditions for magnetic fields. So there are two boundary conditions. Don't worry, we will derive. But just I wanted to give you a brief overview that the normal component of the magnetic flux density, will be continuous throughout the boundary. It will be continuous. That means it will be same before the boundary and after the boundary. It will be continuous. That means B1n normal component will be same as B2n. Just the opposite of the electric field. Because in electric field the tangential component was continuous. Here the normal component is continuous. That is, it is same across the boundaries. In tangential component, the tangential component difference will be equals to k cross an1. Okay, and I understand that you don't understand what is this an1. Okay, and h1t and h2t you can relate with the magnetic field, where the normal components subtraction was equals to rho s, if you remember roughly. So don't worry, I will derive this. Don't have to understand this right now. I will derive this. Okay, so an1 for now is the unit vector normal to the interfacing surface in the direction of the medium 1. Okay, so don't worry, I will derive this, then we will understand this further. So let's first derive the first one, the easier one, that is the normal boundary condition. So in the normal boundary condition, I will take help of this particular simple magnetic field characteristics. What is the magnetic field characteristics? It is B dot ds, closed surface integration of B dot ds will be simply 0. So what I will do, I will zoom in this surface, I will zoom in this interfacing medium, and then I will take a very small cylinder. I will take a very small cylinder which actually encloses a volume. So it is a closed surface, it encloses a volume. So from here what I can say is this B2 and B1 will have two components, right? One will be tangential, another one will be normal. So I will just for now focus on the normal component. So normal component for the top one will be here. Okay, this is my B1n, a normal component for the bottom one, that is B2n. It will be B2n here. Okay, sorry, the eraser is too big. It is B2n. Okay, now the flux due to the normal component, right? Will there be any flux at this curved surface? There are three surfaces. One is this top surface, one, another one bottom surface, two. These are two discs, and this is the third surface, the curved surface of the cylinder, right? The flux is always normal, so the area vector here, the area vector is always perpendicular. So there are I can break this surface integration into three parts. Surface integration B dot ds 1 plus surface integration 2 B dot ds plus surface integration 3 B dot ds. Equals to 0, because this is simply the property of a magnetic field, right? The magnetic flux through a closed surface will be 0. So here what I can observe is that this first surface is the angle between the area vector and the B1n is simply 0. So here the theta is always 0. Theta 0. Here in the second surface, what I can observe is area vector is in this direction and my magnetic field is in this direction. So it is totally a 180 degree phase shift, right? So here the angle between the magnetic flux field density, magnetic flux density is 180 degree. Okay, and for the third surface, here my surface vector will be along the aero cap direction, right? And my magnetic field is always in the normal direction, so it is always perpendicular, right? It is always perpendicular, right? It is always perpendicular. So obviously here my theta will be always 90 degrees. So I can safely say that this one will become what? This one will be B1n and into some delta s, okay, some small surface area s, minus, why it will be minus? Because it is cos 180. Cos 180 is minus 1. So it will be minus B2n into delta s equals to 0. So my B1n will be equals to B2n. So this was rather simple, right? B1n is equals to B2n. This proof was rather simple, just simply taking help of this closed surface integration, same as in the tangential component that we proved, right? There we did the same thing as well for electric field. I'm talking about there del cross, the curl of electric field is 0. That property we used. Now for the second condition, right, it will be a bit difficult, so please listen to me carefully here, okay? And you can put your pen down and try to understand what I am speaking. Later on you can write, okay? So now what you can do is let's prove the tangential boundary condition. Let's prove the tangential boundary condition. So if I want to prove the tangential boundary condition, how I can prove? So one thing is there, that let's say this is the interfacing medium and this is the normal component. Now tangential will actually have two components. One will be this, another one will be this, right? Two perpendicular. So with the help of these two vectors, I can define any vector in this particular plane, correct? Any tangential vector in this particular plane, because I need two combinations. Why? This is the normal component, this is the tangential component. I need three vectors, just like xyz, x, yz. I need three coordinates to represent all vectors, right? So if you want to represent something here, I need the ax cap direction and ay cap direction. Same like here, I need the h1 dash, which will be like, I have assumed that the interfacing medium has a surface current density of k in this direction. I have assumed that. So if I assume that in this direction the interfacing medium, the surface has a surface current density of k dash, so h1 dash t, okay, this is my assumption, will be along the direction of the k, and h1 double dash t will be in the perpendicular direction of k, so that I am able to represent all vectors here. I am able to represent all the vectors that are present here, okay? So that is the important point that I want to stress. I need two perpendicular vectors to represent everything in this plane. That's why I represented two vectors, h1 dash t and h1t. These are both tangential to the normal actually, but there can be two tangentials. One will be along the k vector, another one will be perpendicular to the k vector. Both are tangential to the surface. Same for h2 dash t. Okay. Now this has been defined. This has been written here as well. H1 h dash 1t is tangential direction parallel to k, and this is h1. This will be h double dash t. H double dash 1t is tangential direction perpendicular to k, but this is also in the tangential to the surface. Tangential to the surface, right? I should have written here tangential to the surface. Will I have enough space? That is the question of the century. So I will have to reduce the size. Tangential to the interface. Okay, same thing here as well. Tangential to the interface. Okay. Now, what is AK cap? AK cap is a unit vector that is parallel to K vector, right? So that is what my H dot dl is. So just hold on. Yeah. So my h1t, I can write the tangential component on the surface. I can write like this will be sum of two vectors. One will be h dash 1t, another one will be h double dash 1t. And for the second tangential also, one will be sum of h dash 2t plus h double dash 2t. Okay. So one is this one is the parallel component, and this one is the perpendicular component to k. K is my reference. Surface current density is a reference. Okay. So now let's use the Ampere's law. What does Ampere's law tell us? That now I am mainly concerned about magnetic field intensity, because if you remember there as well, we proved the magnetic electric flux density. If you remember there, right? So here what I'll do, I'll use the Ampere's law. And what does my Ampere's law tell? If I choose a closed curve, and if I take the closed line integration along that curve with the magnetic field intensity, this will be equals to the I enclosed. Okay, the current enclosed within that closed curve, that current that crosses through the surface. Now I can choose two types of closed curve. One closed curve I will choose again rectangle. Why? Because my current is like straight line. Okay, that's why I choose rectangle. And like if you remember, it is like an infinite sheet, and at the top of the infinite sheet and the bottom of the infinite sheet, the field is straight line, straight. That's why I have chosen a rectangle or square, whatever you want to choose. So I will choose a rectangle whose this length will be some finite delta L, and this will be some small length, okay, delta. The height is some delta, and this delta is almost equals to 0. Almost equals to 0. Okay, delta, like I assume the delta is almost equals to, how can I color this? Zero. Okay, this is my delta basically, which is almost equals to 0. Now what can we say? This is almost like an infinite sheet, right? Almost like an infinite sheet. Okay, the magnetic field intensity just at the top is h1 dash t, and magnetic field intensity just at the bottom is h2 dash t, along the direction of k. Okay, so what I can say, I can simply apply the Ampere's loop, right? And what is this is the surface, right? This is the surface that is getting enclosed by encircled by the curve, that is getting encircled by the curve. Can you tell me how much current is actually going into this surface? So how will I explain this? So let's say this is the this is the outside curve. This is the outside curve, and this is the surface enclosed. And my current is in what direction? Current is parallel to this particular line. So current is in this direction. Current is in this direction. So is any current crossing this surface? If current would have crossed, it should have been either in this direction or in this direction, right? Perpendicular. But current is parallel to this. Is any current crossing through this? is any current crossing through this? There are no current crossing. Okay, no currents are crossing through this particular encircled area. Okay, so I can say that no current crosses through the encircled area. Okay, so this will be simply 0. And what is my h dot dl? For the first one, h1 dash t and this orientation is in the opposite direction, right? Like I have assumed some orientation according to myself, and h1 dash t and this is in the same orientation. And like this, again I can break down the left hand side. What will be the left hand side? The left hand side will be like, there can be again 4 sections. First one, second one, I should use some other color, get confused. This is the first one, this is the second one. Where do I write the second, third, or I can do one thing, I can name this. Okay, that's the best thing that I can do. And I'm obviously running out of colors. Where are my colors? Okay, I'm running out of some colors. Let me choose this color. Which one shall I choose? Violet I can choose. Yeah. Okay, so this is A, B, C, D. So it will be equals to AB H dot dl plus BC H dot dl, and if I just copy and paste this thing, CD and DA equals to 0 on the right hand side. Now what is H dot dl AB? AB is somewhere here, so it is something like my H21 is here and my like it is telling the DL direction is in the left hand side. It is totally 180 degrees. So here theta is 180 degrees. Theta 180. Here actually what is happening? My DL is equals to delta, and I have assumed that this length will be negligible just at the top of this interfacing medium and just at the bottom. So this DL is almost equal to 0. So this DL is almost equal to 0. So this DL will be 0. So this whole integration will be simply 0. Okay, and here again my angle, my h1 t dash and this direction of the DL vector is in the same direction. So this angle will be simply 0. Theta will be 0, and again the same reason here, delta DL will be almost equals to 0. So I can rewrite this thing that it will be h1 t dash, this first one will be h double dash, right? H double dash 2t and a negative sign because cos 180 was there, plus 0 plus h, not double dash, sorry, this is single dash, right? Single dash 1t plus 0. This, why is this plus h dash 1t? It is simply because the angle is 0. Cos 0 is 1. So I get my first condition that h dash 1t minus h2 dash t is simply equals to 0. So here what I can say, this gives me that like I can write this like this as well, that both of them are equal basically. So the component that is parallel to the surface current density, right, will also be continuous. This will be continuous. So the tangential component, one of the tangential component will be continuous. What about the other, the perpendicular component? Now I will choose the perpendicular component. Okay, so if I choose the perpendicular component, yeah, just before starting this proof, I just wanted to make a small change, that I have changed my this perpendicular direction, right? The perpendicular of this surface vector k can be in this direction and in this direction. My initial direction was wrong. Now I have assumed my initial direction to be h1 double dash t along this. Okay, the perpendicular direction to be along this. Why? The reasons you will understand later on. Okay, just a small change to make the proof correct. I had to change the direction of this h double dash 1t and h double dash 2t. The reference is now on this side. This is also perpendicular but in the opposite direction. Okay, so we had to make the changes. Nothing will be changed here in this first proof, because we are talking only about the parallel components, but some change will be happening here. Okay, so first of all, we will assume our orientation of this Amperian loop. So now I have taken the Amperian loop that is perpendicular to this K. Okay, so what is the configuration now? The Amperian loop is this, and the current is flowing like this, flowing out of this, right? Flowing into this surface and flowing out of this. And the Amperian loop is like this. So I will just curl my fingers. And my fingers will actually point outwards. Okay, fingers will point outwards. So it is going out of the screen, coming into the screen. Okay, going into the screen. So that's why this is the case here. So fingers will simply be point outwards. Okay, yeah. So it is coming into here, going into the screen, and this is the positive direction. So if I just curl my fingers along this direction, I will choose the orientation such that it is in the positive of K, right? So now if I want to prove the Ampere's law, if I want to use the Ampere's law, again I will break it down into 3 curves. If I break it down into 3 curves, it will be again simply sum of each AB dot dl plus h dot dl bc plus h dot dl cd plus h dot dl da. Okay, now what is the I enclosed here? Can you tell me what is I enclosed? So how is the surface current density? This current of small k is flowing, right? All these small k's are actually crossing the surface now. This particular section, they are crossing this L, right? This dl, delta L length. So total how much current is flowing? Magnitude of K into delta L, and this will be positive. Why this will be positive? Because it is along the direction of the Amperian loop. Okay, please curl your fingers and you will see it is along the direction of the Amperian loop. Okay, it is crossing and it is positive. This is the magnitude that the amount of current is flowing. Now here, if I observe this H1 double dash T and this CD, this AB and H double dash 2T are both in the opposite directions. So again here this will be minus H double dash 2T into delta L. This BC component is, I will choose a very small length. Okay, this is some very small length delta. Okay, and delta is almost equals to, if I can get enough space here, unfortunately I may not be able to, delta is almost equals to 0. Okay, so it is almost equal to 0, so this will be 0. CD, now in CD I am observing that this direction and this direction are same. H double dash 1T direction and the direction of the DL vector both are 0 degrees. So it will be plus H double dash 1T into delta L, and again for the last one it will be 0, equals to magnitude of K into delta L, small length delta L. Delta is this length of this Amperian loop. So this becomes what? This equals H1 double dash T minus H double dash 2T equals to magnitude of K. Okay, now what I am observing, this is the actual boundary condition. Okay, and this is discontinuous about the boundary. What do I mean by discontinuity and continuity? So discontinuity means there is sudden change. Just before this boundary, right? Just below this boundary, the magnetic field intensity was H double dash 2T. Just as I cross the surface, it becomes some K plus H double dash 2T. So it increases by K. So there is a sudden change. That's why it is discontinuous. And here there is no change, right? It is continuous. Along this direction, there is no change. Whatever H dash 2T was, the same is H1 dash T. They are continuous. There is no change by crossing the boundary. Okay, the magnetic field remains same along this direction, but along this direction magnetic field changes. So overall, what is the change? Overall change is this, right? If I just write this down, my overall change of H1T minus H2T. Now remember how I defined my H1T and my H2T. Okay, so my H1T is this, if you remember properly, h1t is this and h2t is this, right? It is sum of the two components, one the parallel component and the one the perpendicular component. Okay, just hold on, I'll check if some important call has came up. Yeah, no call has come up, fine. So now what I can write over here, I can write this is equals to h1t plus h1t minus h2t plus h2t. So this here, what's the important point, this h-1t and h2-2t are same thing, only they are same thing. So this will become 0, this will cancel out, only this one will be left. So this one is equals to what, h1-t minus h-2t. So this is equals to magnitude of k. But what about the direction? What about the direction? So what will be the direction? So if you observe that k is here and h-1t direction is this. Now if I choose another vector that is normal and that is going towards medium 1, let's name this unit vector as an1. Okay, now what are the two vectors? Like that's how I have to find out identify the direction. So this is the k vector and this is the normal vector that is perpendicular, right? Now if I do k cross an1, okay, if I do k cross an1, it is coming towards me. If I do k cross an1, it is coming towards me. So if I do k, like this is my k vector and this is my an1 vector. If I do k cross an1, it is coming towards this. And what is this direction? This direction is the same as the h-1t. It's the same as the h-1t. So I got my h-1t direction by doing the cross product of k and the normal vector that is going towards the medium 1. So the direction will be k cross an1. Now if you identify, the magnitude will be same as magnitude of k, just the direction has been denoted by the cross product. That's it. And this an1 is unit vector. So what is an1? an1 is a unit vector normal to interface towards surface 1, okay, towards medium 1. And this equation, right, you have to remember, sadly this equation you have to remember, you have to identify reference. If you choose 1 here, then this a vector, right, normal vector, there can be two normal vectors, one will be towards medium 1 and one will be towards medium 2. If there is 1 at the starting, you will choose the normal vector towards medium 1. That's the convention. If there is 2 at the starting, you will choose the the normal vector towards medium 2. But we will only remember one formula, and that is this formula, as mentioned here at the starting. Okay, here at the starting, right? So we will only remember these two formulas. Okay, magnetic field you have to remember. It's good to remember because it will take you huge time to derive, and I don't recommend doing that. Okay, so just remember this. We will write h1t minus h2t will be equals to the surface current density cross the an1. an1 is the unit vector on towards medium 1. Okay, so you have to remember this. And normal field normal flux density is same only. Okay, this is talking about the magnetic field intensity and magnetic flux density. And these things I hope you know. This I have taught you very well how to find out the tangential component, how to find out the normal component. Just take the normal, right, with the surface, then you will be able to find out all these things. I will not go much there because all these things have been explained in electric field boundary conditions very well. I will not explain here. Okay, just one more formula. It's good if you can remember. You can skip it also, not an important. How that tan theta 1 upon tan theta 2 relationship same as the magnetic field electric field boundary condition, right? Here tan theta 1 is what, like always remember, theta 1 is what? Theta 1 is the angle with respect to, I have written it, theta 1 is always with the angle with respect to normal. Okay, so if theta 1 is the angle with respect to normal, then tan theta 1 will be what? It will be the tangential is this and the normal component, right? So it will be h1t by h1n, and for tan theta 2 will be same. Okay, so now what I can write is like you can do the simple ratio. Okay, you can do the simple ratio. If I do the ratio of tan theta 1 upon tan theta 2, what will I get? If I do the ratio Yeah, if I do the ratio of tan theta 1 upon tan theta 2. So if I do this, right, tan theta 1 upon tan theta 2, so it will be ratio of h1t divided by h2t, magnitude of h1t divided by h2t into the ratio of h2n divided by h1n. h2n divided by h1n. Okay, so now one more thing I missed here. If let's say my surface current density was 0, so my h1t, the overall tangential component will also be equals to h2t. It will be continuous if I don't have any surface current density. Okay, if the surface current density of that particular interface is 0, then my tangential component will also become continuous. So that is one thing I wanted to take away. So here I can equate this, right? These two can simply get cancelled. Okay, here I will assume that k is 0. So what will happen is this one will become 1 because h1t and h2t will be same, and h2n and h1n, right? Here they are related with this, that what is my h2n is simply if you remember, it was b by mu was equals to h2n, so it will be b 2n by mu. Okay, mu1, and this one is, so this is 2 actually, so this will be mu2 mu1 divided by b1n. Okay, so from here you find out this relationship, that what do you know b2n and b1n are equal, right? You know this fact, b2n and b1n are equal from the boundary conditions. Why did I derive it? Okay, this was the tangential one. Yeah, here b1n and b2n are equal. So b1n and b2n are equal. So first of all you have to say here that you have assumed that your k is 0. Okay, so if k is 0, then what it becomes? Then basically a good tidy relationship you get. What is the relationship? That your tan theta 1 upon tan theta 2 is equals to, this one gets cancelled. So what okay, here I have just written k, this should be k equals to 0. This will be mu 1 by mu 2, or this is equals to mu r1 by mu r2. So this is what I have written here. So this is one tidy relationship that you can know, but you have to identify the conditions. Conditions is the surface current density must be 0. Okay, and theta is measured with respect to the normal of the surface. And obviously this is not Snell's law. Don't get confused with Snell's law, because they get confused with the electric field as well. And here this is not Snell's law. Okay, so now we can solve few basic questions. So let's start with this question. For the boundary at z equals to 0, medium 1 has permeability mu and medium 2 has permeability mu2. This is mu1 and mu2. Okay, mu1 mu2 is given. Okay, fine. And the boundary is at z equals to 0. So I will just draw the surface real quick. I will just draw the surface is already drawn here. Okay, so mu1 is this and mu2 is this. All these things I have written there. And a surface current density is 80 A x cap. So surface current density with direction they will give you 80 A x cap. Ammeter is present on the surface at z equals to 0. At that interface, surface current density is present. So tangential component will not be continuous. There will be a change. Given the magnetic flux density in region 1 is given like this, find the magnetic flux density in region 2. Okay, so you have to apply the boundary conditions. So I have just written the things here, whatever things are required. This is z equal to 0 surface, and this is a1 cap. What will be the direction of a1 cap? It will be in the positive, because what have they told us? Medium 2 is z less than 0 and medium 1 is z greater than 0. So my reference will be medium 1, so it will be plus az cap. That's why I have chosen plus az cap. This is plus. Okay, so now what I can say is, now we just need to find out the magnetic flux density. What things I know? I know what are the boundary conditions. Boundary condition is this, you can write this down to just remember everything, that my b1n will be equals to b2n, and my tangential components h1t minus h2t will be equals to K cross AN1 cap. So obviously I will find out B1N. So I have to find out B2, right? So what will be B1N? B1N will be simply B1 dot product with its own normal vector AN1. Then if I just take the dot product with its own normal vector, I will be able to find out the normal component, and I can directly observe if it is a simple surface like z equals 0, the normal component will be simply this one will be the only normal component, right? Az cap. All the other will be tangential to this surface, correct? So still I wanted to solve in front of you. So this will be 2ax minus 3ay plus az cap dot az cap, right? Because an1 is az cap. So only the, as mentioned previously, it is only 1, and obviously this is 1. This is talking about the magnitude of the normal component. What about the actual vector? It will be magnitude of V1 and N1. So this will be simply equals to AZ cap, right? Simple AZ cap. And this will be equals to my B2N as well. So B1N and B2N are same. So one component has been found out. What about the other component? So now I have to find out the tangential component. So first of all, I write B2T. What will be B2T? B2T will be simply, not B2T, sorry, B1T. B1T will be simply B1 minus the normal component. If I just subtract the normal component, I will get back my tangential component. And like from here, I can directly observe that the tangential component will be these two, right? Here, can you observe this thing? That there are two tangential components, one along the x, one along the y. So there can be two tangential components, right? Okay, so that's how this analogy came up, that there are two tangential components. So this will be simply 2ax minus 3ay. X minus 3ay. So this is my normal, this is my tangential component, and I will write from this, I will write my h1t. H1t will be what? B by mu, simply B1t by mu, okay, by mu1 basically. So this is my h1t. I will write this later on, don't worry. Now I will use this boundary condition, that my h1t is this B1t by mu1 minus B2t by mu2 is equals to K cross AN1. What is K? K is 80ax. K is 80ax. So it will be 80ax cross AN1 is AZ cap, right? AN1 is simply AZ cap. This is the reference, and this is how I will write always. So this formula I have to remember, okay? But how to remember, that also I explained. Everything has been derived. So remember, this is in like this is in millitesla, right? Remember, all this is in millitesla. Okay, this is in millitesla. So I will put the units at the end. Okay, we will not do anything with the units right now. So my B2T will become what? B2T will be equals to mu2 by mu1. So see how am I solving? This is how you solve in the examination hall as well. You don't put the values, you put the values at the end. This will be B1T minus 80. Now remember, what does AX cross AZ means? AX cross AZ is minus AY. So this becomes minus, and on the, if it goes on the left hand side, it becomes plus. So this will be plus AY, okay? So this minute adjustment you have to do. So now we can simply solve. What is mu2 by mu1? Mu2 by mu1 is 7 by 4 simply. So this will be 7 by 4. And what is V1T? V1T I have just written. It is 2ax minus 3ay plus, okay, one thing I forgot is that if I multiply mu2 on both sides, this also will get multiplied by mu2. This one I missed. So this also will be mu2 times, right? Something mu2 times this. Okay, so this also will be mu2 times this. Mu2 is simply 7 into 10 raised to power minus 6, and this anyways is 10 raised to power minus 3 actually. So can I do anything? What I can do is I can just write here mu2 only. I can do this. I can keep this mu2. Why am I keeping this mu2? Do I need to? Okay, yeah, because I cannot keep this mu2. I have to replace everything. 0.7, and remember this is in millitesla, so this will be 10 raised to power minus 3. Here this is in millitesla, correct? So this also will be equals to 10 raised to power minus 3 AZ cap. This is in millitesla. So this becomes 7 into 10 raised to power minus 6, correct? 7 into 10 raised to power minus 6 into 80. This actually becomes quite small. I'll just quickly calculate this. If I calculate this quickly, right? If I convert everything into milliteslas only, so if I convert everything into milliteslas, so one of the 10 raised to power minus 3 will go away. So this one will become 7 into 80 into 10 raised to power minus 3 AY cap. So what does it become actually? 7 into 80 divided by 1000 is 0.56, and this one is 0.56. This is in millitesla, remember this is in millitesla, and this one will be 7 by 4 into 2, 3.5 AX minus 7 by 4 into 3, 5.25. A Y cap. So overall this is, remember this is in millitesla, so that's how you have to be careful with the units as well. So I'll just keep it as millitesla only. I'll not change anything. Keep it as millitesla. So this one will be 3.5 AX plus 0.56. Okay, 1.12. This is minus 4.69 A Y cap. So basically my overall B2, right, will become B2T plus B2N. So this will be 3.5 AX. This is the tangential component AY plus AZ. Okay, the normal component remains same. Remember this is in millitesla. So this is how you solve these type of questions. Just you have to be careful with the units. You have to be very careful with the units. Okay, so you can observe that this vector and this vector both are perpendicular to K. So I have two vectors that are perpendicular to K, and this vector is parallel to K. And if you observe that the vector that is parallel to K, it doesn't change actually. It remains 3.5 in the B1 as well. If you see B1 as well, it was okay. Sorry, made a mistake here. This is AX cap, right? What was the case? Okay, yeah, the vector that is parallel to K. Just hold on. The vector that is parallel to K, that should not change actually. That is perpendicular, that should change. Yeah. So what I've changed here? Oh, sorry. Actually, this also will change, because here, right, this is actually that mu term is there. The magnetic field intensity will definitely remain same. Okay, magnetic field intensity will definitely be continuous. Obviously, the magnetic flux density is a proportional relationship, so that's why it changes. So that's the thing. Let's solve another question. This question is also very interesting. So we have been given a surface, okay, and surface current density is also K, and the equation of this interface is given between the two mediums is shown. Okay, equation of the interface between the two mediums is shown. It is observed that the function increases if we move from surface 1 to surface 2. So this function actually increases its value when we move from surface 1. Surface 1 is this, medium 1 to medium 2. So this should be medium 1 to medium 2, not surface. Medium 1 to medium 2. Now, according to the values of xyz, so if the magnetic field intensifies, if the magnetic field intensities for each of the medium is given, so magnetic field intensities are given, then find alpha. Alpha is here, surface current density, and the angle between B1 and B2 that it makes with the normal interface in the direction of the medium 1. So medium 1 is the normal interface that they are given. They are asking me the angle as well. So first of all, how do you find out the gradient of this thing? So they are telling me, as I am moving from surface 1 to surface 2, this scalar point function is increasing. Okay, so as I am going from 1 to 2, my scalar point function is increasing, that is phi is greater than 0 if I am going from medium 1 to 2, and phi is less than 0 if I am going from medium 2 to 1. So what was this information for actually? This information was to just to identify the direction of the normal vector. That's why this information was present. So for phi greater than 0, if I'm moving from medium 1 to 2, this function is increasing. That means if I take the gradient of this function, if I just take the gradient of this simple function, I will get, what does gradient give me? Gradient gives me the direction normal which towards which I am increasing, towards which the scalar point function is increasing. So it will give me the direction towards medium 2. But what I want the direction towards medium 2, towards medium 1. So what I will do, I will find out the gradient of this function that will give me the direction towards medium 2, and I will just multiply a negative 1, so that will give me the direction towards medium 1. So that information is very important, and GATE exam can play with these small details. So the gradient of phi will basically give me, where did you go, will basically give me the I have to divide by magnitude as well, magnitude of grad of phi, give me the an 1 to cap. Okay, so what is grad of phi? It will be simply 6ax plus 2ay minus 3az. This is the grad of phi. And what is the magnitude of this? It is 36 plus 440, 49. So it will be under root 49, that is 7 simply. So this is an 1 2. But what do I want? But I actually want. So I will just write down specifically few things. So actually I have found out the direction, this, right, a n 1 2, but actually I want the direction this a n 2 1, coming from 2 to 1, going to 2 to 1, finally is 1. So what I will do, I'll just multiply a negative. So I know a n 2 1 will be minus of a n 1 2. So a n 2 1 vector will simply be minus of 6ax minus of 2ay plus of 3az divided by 7. So this was the only decoding thing about the question. After this, all things are simple. So after this, you just have to apply the boundary conditions, and you will be able to identify the surface, the values. Okay, so only this was the interesting part about the question. So how will you solve? So what you can do is, you have now identified this thing, right? So what you can do is, you can apply the normal boundary condition. If you apply the normal boundary condition, the normal component must be same. The normal component of these two things must be same. Okay, normal flux density, that is. So if I want to find out the first thing, what I will do, I will say that B1n equals to B2n, or I can further write this as mu 1 h1n must be equals to mu to h2n, because magnetic field intensities have been given and not flux densities. So what is what is known to me? H1 is known to me, right? So h1 is this. So from here I can write what is my h1 n. It will be simply the dot product of this vector with h1, right? Magnitude of h1n will be h1 dot an 21. So if I take the dot product, what will I get? This will be minus 60, this will be minus 2, and this will be plus 36 divided by 7, and the direction will be along the direction of an1. I will not write the direction right now. I am just concerned with the magnitude, because magnitude must be same and the vectors also must be same, but mainly magnitude must be same, right? So this is equals to what? This is minus 62, so 6 is 56, 26. So this is minus 26 by 7. Okay, and what is mu1 and mu2? Mu1 and mu2, mu1 is mu naught and mu2 is 2 mu naught. So I know mu1, so I have to find h21. So this will be mu1 by mu2 into minus 26 by 7 equals to h2n. And what is h2n? I can find out the h2n as well. H2n is what? H2n is again the dot product of this and this, right? So it is minus 6 alpha, then minus 2 times minus 5, so it will be plus 10, then it is plus 3 times plus 4, so it is plus 12, divided by 7. So, and this is it, right? This is the dot product basically. This is the magnitude simply. This is the normal component magnitude. So this should be equals to here magnitude of h2n. So now 7 will get cancelled, and mu1 by mu2 is simply mu naught by 2 mu naught. So it will be 1 by 2. So it will become minus 13 equals to minus 6 alpha plus 22. So 6 alpha equals to 13 will be added 35. Okay, and your alpha will come out to be 35 by 6. Okay, if I do 35 by 6, I will get 5.833. And will it be unitless? No, right? It won't be unitless, because it is the same unit as magnetic field intensity, which is in ampere per meter. So it will be ampere per meter. So first one is solved. So what about the next part? Next parts are easy only. Next part, this was the first part. Okay, yeah, second part, surface current density. How do I find out the surface current density? Again, you have to apply the tangential boundary condition. What was the tangential boundary condition? It was simply h1t. I will apply my tangential boundary condition, what I chose as reference. It is h1t minus h2t equals to k cross an21 going towards the surface one. So what is h1t? So I have to find out h1t now. So if I want to find out h1t, simply I have to subtract the normal component from the h vector. So that is a task. Okay, that is a task. So what is h1? H1 is this only. H1 is this. Okay, And what is my h1n? h1n, the magnitude is this, correct? The magnitude is this, not the magnitude, like the, and the, what will be the direction? This is not the magnitude. Actually, magnitude can never be negative. This is just telling me about the direction, because okay, I will just talk about the direction only. This is not the magnitude actually. What this is I should have written this with like this. That's the best way to represent this. Okay. an21. So this will be minus 26 by 7 into an vector. An vector is, what is my an1? Normal vector. This is the normal vector, right? So like it will be a right with me. So what I'll do, I'll just quickly compute all these things, right? Do the computations and then show you, because it will just be a waste of time. Because what you have to do, you have to just apply this boundary condition, right? Just apply this boundary condition, then you'll be able to solve it. So I'll just quickly do these computations and then come back. So I have just solved the second question. So in the second question, like one small change I can do is, if you observe here the tangential boundary condition, right? If I'm at this point here, so what is my h1t and h2t? h1t and h2t are something in this direction. So if I do h1t cross my a21 vector, okay, h1t cross a21 vector, I will get a vector that is parallel to both h1t and the normal vector. What is that vector? That vector is back again k, because these three are mutually perpendicular. If I do h1t cross a21, I will get a perpendicular vector that will be both perpendicular to h1t and a21, which is the k direction of the k vector itself. Why? Because these three vectors are mutually perpendicular to each other. So here I have written this condition: k cross an1, h1t minus h2t is equals to k cross an1. Now what I can do, if I just take the subtraction of these two, h1 and h2, and then take the cross product of a21, I will get a vector that is k vector. Okay, so sometimes that relationship will also be useful, so you will use that as well. So here in this tangential component, you can write down another relationship that is sometimes very helpful. As these three are mutually perpendicular to each other, you can write h1 minus h2. If I take the cross of a21, not a21, an1, I will get back my surface current density. Okay, so this is one good relationship that you should know. So this will help out here in this question. So here we are doing the same thing, because we know the magnetic field intensities. I will just do the subtraction and then I will be able to find out the surface current density. I don't need to separately find out the tangential component of each of these two mediums. Okay, so if you solve using that, if you do h1 minus h2t and then take the cross product, you will get your surface vector something like this. Okay, your surface vector will come out to be this. Now for the third part is what? I have to find out the angle b1 and b2 makes with a normal interface. Okay, so I have to find out theta 1 and theta 2. So again, if I just do this thing, that my like if I derive this thing, right, so it will be, this will be something like my b1 vector, this will be my b1t tangential, and this will be my normal component, right, b2n. Okay, and this is the theta 1 that they are asking me to find out. So how do I find out this theta 1? So you can simply use this relationship, that your tan theta 1 equals to what? Normal component magnitude, tangential component magnitude b1n divided by magnitude of b1t divided by magnitude of b1n. Now this will be equals to what? This will be same as, they are related with the same constant, h1t divided by magnitude of h1n. Okay, so this will be equals to, tan theta 1 will be equals to this becomes B1T, H1T, H1N. So okay, what is H1T magnitude? H1T magnitude is H2N magnitude, H1N magnitude is this only. Okay, 26/7. So it is 20. The magnitude of this will be 26/7. So this will be 26/7. What about the other component? So for the other component, I have to find out the magnitude. So simply what you can do, you can just subtract. You can find out your H1T from this particular relationship, or what we can do, we can directly find out this relationship, right? Either instead of doing this tan theta 1, the better thing that I can do is this one. I'll do this. The better thing, I know what is my H1N, B2N, right? I know my, sorry, not B2, sorry, this is B1. Sorry. I know what is my B1N, that is, it is related to H1N. So I'll write here, right? Instead of writing B, I can, okay, as they have asked B actually, this B will be same as H only. This B will be same as H. All this will be changed, right? So what I can do, I can take the cos theta. Okay, so my cos theta cos theta 1 will be equals to magnitude of H1N divided by magnitude of H1. So I am just reducing my computation. So this will be equals to what? I know this one and I know this one, because again I have to find out the tangential, and that will be difficult for me. So I don't want to go to that. So my H1N is this vector. Okay, so magnitude will be 26/7. 26/7 divided by the magnitude of H1 vector, right? Magnitude of H1 vector is this, which is already known to me. That is 10 square plus 1 square plus 12 square. So it will be 10 square plus 1 square plus 12 square whole under root. So this will be equals to what? This will be 10 square plus 12 square plus 1 whole under root, and into 26 divided by 7. This is 0. Cos inverse. So theta 1 273 degrees. Okay, theta 1 is this. So theta 1 I have found out. What about theta 2? Now do I need to compute the H2T and all those things? No. What I can do is, again, you can use the same formula, cos theta 2, or you can use this formula, right? But there is some surface current density, so we cannot use that formula. We cannot use tan theta 1 upon tan theta 2. We cannot do that, right? You cannot do this tan theta 1 upon tan theta 2. Just hold on. Equals to mu r1 divided by mu r2. You cannot do this. Okay. Why you cannot do this? Because my K, there is some surface current density, right? K is non-zero, so I cannot do this. So again, I will use the same formula again. I will copy all of these things. All of these things I will copy. Okay. So basically, all of this will get changed to B2. Cos theta 2, theta 2 to this one will be same. Magnitude on the normal component will be same, but the this component will change. This theta will also change. So here I know the magnitude of the normal component, right? They are same because normal component is continuous, so it will be same only. H2N will be same here. So, but what is the actual component? What is the magnitude of the actual component? So this magnitude will be same, 26/7 only. Okay, no, this magnitude won't be same because it is getting differentiated with the normal, right? So yeah, actually H2N will be this, right? This is not magnitude, this is just H2N vector. It is minus 26/7 into mu1 by mu2, so it is 26/7 by 2 into, it was mu1 by mu2, which is by 2, so that's why it will be 13 by 7. Okay, next the actual magnitude. So the H2 comes out to be what? This alpha is 5.33, so my H2 value is what actually? 5.833 ax cap, and it is minus 5 ay cap plus 4 az cap, minus 5 ay cap plus 4 az cap. So this, if I copy this, if I paste this here, so now we'll write the magnitude. It will be 5.833 whole square plus 5 whole square plus 4 whole square. So this will be equals to what? 5.833 whole square plus 5 whole square plus 4 whole square. If I take the whole under root, it will be 29.438, and this will be 26 divided by 2 divided by 7 divided by, this is 13 by 7. So this 29.438 cos inverse, this is my cos theta 2. Okay, and my cos theta 2 almost comes out to be 86.38. okay, just be careful, there is a extra half here, because this h2n is not simply equal, like h2n is equals to h1n. There the mu was getting cancelled. Okay, that's why it didn't matter if this was okay, it was 26 by 7 only. Okay, it was 26 by 7 only, but here mu is not getting cancelled because the magnetic flux density is same, magnetic field intensity is not the same. Okay, so you have to be just careful about that. I will just quickly cross verify whether everything is correct here or not. Here my h2n is simply mu1 by mu2 is 2 mu naught, so it will be half of this, so it will be 13 by 7. Fine. So from here I get back my value as alpha is 5.833 whole square. Why is this coming so big? This should come so big. 5 square plus 5 square plus 5 square, it is like 125. Under root of that will not be that much big. Okay, I have made some mistake here, I think. 5.833 whole square plus 5 square plus 4 square. Yeah, that is what I was thinking, that I must have made some mistake here. So it is actually 8.66. Now if I divide, this is just 1 into 13 divided by 7, then if I do cos inverse, it will be 77.6. okay, yeah, that was a mistake. Basically this is 0.214 and this comes out to be 77.62 degrees. So this will be the answer. Basically the first one will be 76.273 and the next one will be 77.62 degrees. This will be the angle that the magnetic field intensity and the magnetic flux density, as they are just related with the coefficient, they will make with respect to the normal. Okay, so let's do one more question. So there is last question that we have to solve. So we have the plane acts as an interface between two mediums. Z equals to 0 is the interface basically. Z less than 0 is medium 1, Z greater than 0 is medium 2, and me1 and me2, all these things are given. B2 is given. Okay, the interface has a surface current density, this, it is not 0, it has a surface current density equals to this. Determine B1 and H1. Just simple question only, not that difficult. Just you have to how to like use the boundary condition, that you have to understand. Just hold on, I will check if everything is fine and recording. Yeah, everything is recording fine. Yeah. So here first of all you have to draw the surface. Basically if I just draw the surface, this is my Z equals to 0 surface, correct? So medium 1 is Z less than 0, so this is my medium 1, where my medium 1 has mu1 equals to 6 mu naught, and b1 I don't know. Okay, and medium 2, let me use some other color, medium 2 mu2 equals to 4 mu naught, and b2 I know, the magnetic field of medium 2 I know. The magnetic field on medium 2 is simply 5ax plus 8az. Okay, this is in millitesla. Now we will find out b1 and h1. So obviously we will do the normal component. So here, right, I don't need to do that cross thing. I know what is a normal component. Normal component about the medium, my reference is again going towards medium 1. So this is z less than 0, this is z greater than 0, correct? That is what is mentioned to me. Z greater than 0 is medium 2, z less than 0 is medium 1. But my reference will be z less than 0 because I will always go towards medium 1. So my an1 will be minus az cap this time. So this you have to understand very carefully. What is my normal direction of the normal vector? Other things will be sorted out. So now you can simply solve this, right? What you can find out? So you can simply find out the normal component. The normal component of b1n and the b2n must be same. Okay, so the normal components are same. What can I comment about? So I can comment that what is the normal component of b1, the b1n normal component, because I know b2, right? What is the b2n normal component? It will be simply b2 dot an1 then a1 at the outside, just to give it the vector direction. Okay, so does it have any normal component? Yes, it has a normal component. It is plus 8az, but it is opposite to my reference, so it will be minus 8az. You can do the computation, you will get as minus this will be an, okay, not minus, actually this will be plus only. Okay, sorry, this comes out to be if I just compute this thing, what does this come? So this b2 dot an, just you have to do the computations here very carefully. Okay, so b2 dot an will be, b2 is 5x plus 8az. Okay, then I have to do the dot product with minus az, and obviously at the outside I have another minus az. You have to be very careful here. So this will be simply equals to this dot product will be 0, this will be minus 8, and at the outside also I have a minus 8 minus az. So overall this will become plus only. Okay, so you have to be careful about this. So your normal component of b2n will be plus 8az. So this thing you have to be very careful. Okay, you cannot mess up here. This thing you have to be very careful. It will be plus 8az, and it will be simply equals to my b1n as well. Okay, you're understanding. Just I'm doing the dot product, so you have to be very careful here. Okay, according to the dot products. Normal component is done. What about the tangential component? So tangential component, the h1t minus h2t should be equals to k cross an1, correct? So in electric field we could have done anything because there we could have taken any reference, but here I recommend you, highly recommend, whatever reference I have chosen, you take that reference, you don't change your reference. So b1 is given, right? So what is b2t basically? What will be b2t? b2t will be this component, right? Only this. The normal component is this. The tangential component will be this. So I can directly say here my b2t will be b2 minus the normal component, so it will be simply 5ax. Okay, so all of this I can convert in terms of magnetic flux density. So this will be b1t by mu 1 minus b2t by mu 2 equals to k. What is k actually? K they have given me, right? Direction of k is in the ay cap direction, 10 raised to power minus 3 by mu naught. So this will be 10 raised to power minus 3 by mu naught ay cap direction cross A in the minus AZ cap direction, right? AY minus AZ cap. So you have to be very careful with the vectors here. So I need to find out B1T, right? B1T will simply be equals to this will go there. So B2T into mu1 divided by mu2, and this one will become what? Y cross AZ is plus AX, but there is a minus sign. It will be minus. This will be plus. This will be 10 raised to power minus 3 mu naught into mu 1 into minus AX. So you have to take care of the directions here. So what is mu1 over mu2? Mu1 is 4 mu naught, mu1 is 6 mu naught, and mu2 is 4 mu naught. So it will be, this is 4 mu naught, right? 6 by 4, and B2T have already computed. It is 5 AX plus it is 10 raised to power minus 3. Remember one thing, that this is in millitesla, so this also will get absorbed here, right? As this is in millitesla, I can simply absorb it. So like I'll just cancel this. I'll write here, this 10 raised to power minus 3 will get values due to millitesla. Okay, mu1 is how much? 6 mu naught, right? So this will be 6 times minus AX. Okay, so this will become 1.5 into 5, 7.5 minus 6 AX B1T. So it will become 1.5 AX millitesla. This is in millitesla. So overall, what does my magnetic flux density becomes? It becomes 1.5 AX, and obviously the normal component will be same, that is plus 8 AZ in millitesla. What about if I want to find it out in terms of Henry H1T, right? What is H1T? H1T will be simply B1T divided by mu1. So if I divide by mu1, it will be 1.5 divided, so just the constant term will be there, that is B1T divided by mu1, that is 1 by 6 mu naught into 1.5 AX plus 8 AZ in milliampere per meter. Okay, so this will be the answer to this particular question. Like, I think your answer may come differently, because somewhere in the middle you would have assumed the direction to be wrong, or you could have assumed the values, right? This millitesla you wouldn't have been able to convert it properly. So why am I solving this in front of you, taking so much time doing all the calculations in front of you, so that you can learn from me, okay? So that you can understand how to do the calculation, how to do the computations in the examination hall. Trust me, this much lengthy question won't come. One of the section of this particular question can come, okay? One short section of this question can come. But if you learn these difficult questions, right, then no one will be able to, this type of question no one else will be able to solve, but you will be able to solve, and that will give you the added advantage. So with the help of this, we actually have finished our magnetostatics portion, okay? So it was very lengthy, and we finished it, tried to finish it with more speed, because we gave so much time to electrostatics to understand the basics. So your basics were already cleared, that's why I went a bit fast over here. And from the next lecture, we'll start with electromagnetic induction, basically time varying fields. So if I vary my magnetic field, then what type of phenomena I observe. So that phenomena we use everywhere. That is what is being used currently. That is the technology that is being used. So that we will study in the next lecture. So I hope you enjoyed this part. I hope you enjoyed the boundary conditions. Trust me, the way you have learned boundary conditions, you would not have learned previously, and many your friends also will not learn these type of boundary conditions, right? Because they just tell you the direct condition. This condition, just one page they will tell you. This is the page that will tell you, okay? I am saying it to you. This page they will talk about, okay? This is the page only they will show you that, okay, normal boundary condition is this, tangential boundary condition is this. But why, they will not tell you, okay? But I have proved I've proved everything very clearly, okay, with all the proper conventions. So we have solved very difficult questions as well. So I hope you enjoyed this lecture, and I will see you in the next lecture. Until then, happy learning.